Hello there. My name's Rod Burns, and I'm VP of Ecosystem at Codeplay. I'm going to talk to you about how our teams are bringing together open standards and open source technologies to enable complex applications for a range of processors. Algorithms such as convolutions and pooling involve running operations on matrix and vector data structures. It's these operations that can be executed efficiently on processors that are designed to allow many common operations to run in parallel across many cores. This has become a common use case for GPUs in recent years, but companies are also looking at ways to develop more specialized processors to tackle the performance challenges of modern AI applications. During this section, we'll work through a demonstration of the running an accelerated neural network application using RISC-V on the SPYCL simulator, and how this same software stack can be adopted to other processor types. We talk about offloading work to either a GPU or other processors we might call XPUs. A GPU or XPU can process a lot more data at the same time because of the larger number of cores that are available. This makes it possible to do things like matrix multiplication much more quickly than on a CPU. However, in a heterogeneous environment, the CPU is used as a host, which means it's used to control the transfer of data and instructions to the GPU or XPU. This is what's known as offload, where the CPU offloads the execution of work to the GPU or XPU. The host CPU is optimized for latency, and the GPU or XPU is optimized for processing large amounts of data. SYCL and OpenCL are open standard APIs that enable code for heterogeneous processors. Codeplay has been involved in helping to define the SYCL and OpenCL standards for the past 6 years. SYCL in particular offers a non-proprietary alternative to CUDA, and there are existing communities working on projects, libraries, and frameworks with SYCL and OpenCL. The NASA laboratories in the US, CERN in Europe, and many other organizations are using SYCL to deploy applications to the most powerful supercomputers in the world. Go to sycl.tech/projects to find out about some of these. What Codeplay is seeing from large organizations writing complex HPC and AI software is that they're looking for software tools that bring programmability. What that means is that they have the flexibility to extend the AI operations that are supported by frameworks on specific processors and fuse multiple operations together to reduce memory access. This kind of flexibility is only possible using a programming model that gives developers this ability. The research team at Codeplay has built a neural network application written in standard ISO C++ that uses SYCL-DNN, Eigen, and SYCL-BLAS, all open source libraries that are written using SYCL and implement the algorithms required for this layers of this network. The application uses the VGG16 convolutional network to demonstrate running an end-to-end inference model through the RISC-V SPYCL simulator. By using the SYCL-DNN library, it's possible to call various neural network operations like convolution, softmax, and maxpool. SYCL-DNN provides accelerated kernels for each of these operations, and in turn uses tensor operations from Eigen, an open source linear algebra library also used by the TensorFlow framework. These operations can offload work to the cores of a RISC-V processor supporting the RISC-V extension. I'll now run the demonstration application. Calling this command line script executes the binary for our demo program and passes it an image to be classified. The RISC-V SPYCL simulator is running in the background, so this is the equivalent of running on real RISC-V hardware. In this example, it finds an American Staffordshire Terrier. The demo is currently being extended to include ResNet and other networks by our research team. You can see from this graphic that the VGG network passes an image through a series of operations to run the inference. The SYCL-DNN library provides optimized operations for 2D convolution, pooling, and transform for the softmax pass, and SYCL-BLAS provides a gem operation required for the fully nected pass. These libraries make it straightforward for developers to call these functions with the appropriate inputs. These high-level libraries provide an optimized set of primitives used by neural network applications, and software developers rely on these to be tuned and optimized for the processors they are targeting. So we have a classifier application using the VGG network running with SYCL, but how does it work under the hood? I'll now talk about how our Acheron platform translates the C++ code written by our research team into lower-level instructions that can be understood by a processor. Let's start with a bigger picture look at the technology stack that is needed to drive this demonstration application. This graphic shows how the different parts of this demo fit together. The Akaran platform provides some of the components for this demo. The application developer writes code that calls operations from the open source SYCL DNN library that has kernels tuned and optimized for processors. In this case, the SPIKE RISC-V simulator, but equally this could be a real RISC-V cores or indeed a processor of your own design. The Eigen library supports SYCL DNN by providing optimized kernels and kernel fusion for tensor operations. This code is all passed to Compute CPP and is compiled along separate paths. The operations used by the neural network are too complex to show here, so I'll use a vector addition to demonstrate this journey from C++ code onto the SPIKE RISC-V simulated processor. Here we have a small SYCL program. The code on this slide contains both code that will run on the host CPU and on the accelerator device. The RISC-V Vector processor is the accelerator device in this walkthrough. The program is a simple vector addition. First, we create a queue to manage code sent to the device and buffers to contain the data we'll process. The CL SYCL range num of items will be used to represent how many parallel work items will execute on device code. In this example, we have one work item per index in the input vectors. All of this code runs on the host CPU. After this, we have a device queue submit call that we can pass a lambda to. The code within the lambda will run on the RISC-V vector processor. The most interesting part of this is the body of the kern lambda. This contains code for the vector addition. We pass this kern lambda to the parallel for function, and that is how the device compiler knows that it needs to handle this piece of code. The semantics of the code are that this lambda gets executed in parallel num of item times, and our device compiler exploits its knowledge of these semantics to generate efficient device assembly. First, the device compiler will compile a single instance of the code that will run in parallel. Here we have the LLVM intermediate representation for that code from our example. Within the intermediate code, you can see two loads, an fadd, or floating point add, and a store, i.e. all the parts of a vector addition. You can also see that on the line that begins with a %1, a call to a function getGlobalID. The name is mangled because that's how type information is handled within the compiler, but the unmangled name is getGlobalID. This is how we arrange for each parallel instance of this function or work item to process a different value. This is also how we can exploit the parallel semantics of SYCL to efficiently compile to RISC-V vector instructions. The parallel semantics of this function is SPMD, single program, multiple data. That is the same single program that will run multiple times on multiple pieces of data. In this example, that was achieved using the getGlobalID call, which will return a different value for each instance of the program. This means that we can compile a set of work items to a SIMD, single instruction multiple data packet. Each packet will execute a set of adjacent work items in parallel on a single vector unit. Now you can see how the LLVM intermediate representation looks after we perform that transformation. This is still the vector addition. You can still see the two loads, the fadd and the store, but now instead of operating on a single unit, it's working on a vscale by one set of inputs. If we were compiling for an architecture with a fixed vector width, such as AVX, this would be a fixed vector size instead. But the RISC-V vector ISA lets us compile to a scalable width. Now that this program represents vscale work items, the runtime code will automatically know to execute this fewer times. Finally, we compile the intermediate representation to actual RISC-V vector instructions. You can still see the two vector loads of 32-bit elements, VLE32, the vector floating point addition, VFAdd, and the vector store of 32-bit elements, VSE32. The scalable vector width is handled by using the vsetVLI instruction. We set the number of elements to be processed, and it returns how many 32-bit elements a single physical vector can contain on this hardware device. We then loop around this an appropriate number of times, and we've achieved our parallel vector addition. This same approach scales up to the operators within a machine learning graph, but the amount of code involved certainly would not fit on a slide. So in closing, understand that this demonstration is being adapted for other neural networks, such as ResNet. And this is made straightforward because SYCL allows developers to use existing common software frameworks and libraries. The fundamental operations required for neural networks already exist, and SYCL's flexibility enables new operations to be added to these libraries. This demonstration was built using open standards and open source software, with current support for the RISC-V spike simulator. But the beauty of this approach is that by implementing the low-level support for other processors, the whole stack can be used by application developers. If you want to try this out on your own computer and examine the instruction output for the more complex neural network code, go to this URL and download the package.